Swayam Prabha. Digital India. Educated India.
Hello, welcome to module 53 of NPTEL NOC on Point-Set Topology Part-II. The title of this today's talk is an application to quotient maps of what? Of the exponential correspondence that we have studied last time. A natural question that arises with respect to the quotient topology is the following. Suppose you have two quotient maps Qi from Xi to Zi, I equal to 1 and 2. Is the product map Q1 cross Q2 from X1 cross X2 to Z1 cross Z2 a quotient map? So, you may be surprised that in general this is not true. See, surjectivity will be still there, continuity is still there. If Q1 or Q2 is a Q1 and Q2 are open maps, the product is also an open map. But in general, we have to study other quotient maps. The quotient, not all quotient maps are open maps, right? So, here is the satisfactory answer. In any case, this question was actually raised in part 1 itself when we were studying quotient maps. So, today we will have a satisfactory answer. Q1 cross Q2 can be written as Q1 cross identity composite identity cross Q2. Okay, this is just a set theoretic fact for any function of a product sets. So, if I have shown that each one on the right hand side is a quotient map, composite of quotient maps is a quotient map. Therefore, Q1 cross Q2 will be also a quotient map. Therefore, question is reduces to the special case when out of Q1 and Q2 you assume one of them is an identity map. By symmetry, whichever one you assume, it is the same thing. Q1 cross identity or identity cross Q2. If you show for all Q2, okay, this is true, that's fine. It will also imply it is true for all Q1. So, what we shall do is that we shall show that if X is locally compact regular space, then for any quotient map Q from Y to Z, Q cross identity of X is a quotient map. Okay, so this is the condition, locally compact Hausdorff's. Okay, locally compact regular. Locally compact Hausdorff implies locally compact regular. So we will take this step in. We will take this one, locally compact regular. Let us recall a fact about quotient topologies. A continuous surjective map of topological spaces is a quotient map if and only if it satisfies the following property. Given alpha from A to B, that's a continuous surjection is given. One is a quotient map. or when the topology on B will be a quotient topology. This is the condition. For every topological space W, every function G from B to W, some set theoretic function, if the composite is continuous, then G must be continuous. If G is continuous, then the composite is continuous, is obvious. Because composite of continuous functions is continuous. Here, it is the other way around. If this is satisfied for every G, then alpha will be a quotient map. So I am not going to prove this one. This has been proved and used several times. I am going to use it now. Starting with Q cross identity, which is surjective and continuous, under the hypothesis that the topological space X is locally compact and regular, we are going to prove that this thing is a quotient map, right? What we need to prove? We need to prove the following condition. Take any W and any map G from Z cross X to W. Okay, any function, such that when you compose it with Q cross identity, that is continuous. Okay, then G is continuous. This is what we have to do. So this is the diagram is given. Y cross X to Z cross X, Q cross identity. We want to prove this is a quotient map. So take any W and any G here. This G will be continuous if you assume G composite, this Q cross identity, and then composite with G, that is continuous. That is what we have to do. Okay, now how do you use the exponential correspondence? When you have this function continuous, we know this is the same thing as saying that there is a map from Y to set of all, space of all continuous functions from X to W. Okay, X to W. All right. See, what is that map? It is given by the exponential correspondence. This F is replaced by F hat here, given by F hat of any point Y. The same thing is F of Yx. So you get a continuous function. Okay, so exponential correspondence says that F hat is continuous if and only F is continuous. Okay, so this we are going to use now. So once you have this, look at this also here, which is just Y to Z, the given map Q. Okay, Z to G, you have some function here, G hat. Okay, Z cross X to W. We have some function here. I don't know whether it's continuous. But what I know is G hat composite Q is F hat. This is just a set theoretic fact. Okay. G hat of Z is defined as G of operating upon any X is G of ZX, right? So for that reason, this will be this G hat composite, this Q composite G hat is F hat. Okay, so this is continuous, but I have started with Q as a quotient map. Therefore, G hat is continuous. But once G hat is continuous, exponential correspondence says that this G is continuous. The proof is over. Okay. So proof that product of any two quotient maps is a quotient map is still not yet over. That is not true. If one of them is locally compact, Hausdorff, or locally compact, regular, then it holds. This is what we have done. So now we can use that to just give you satisfactory answer. This is not a if and only kind of answer, okay, but it's a useful thing. Suppose you have y1 cross y2 to z1 cross z2, you have q1 cross q2. So two quotient maps, and then you have taken the product. You can come to Z1 cross Z2 from here in two different ways. Q1 cross identity of Y2, then followed by identity of Z1 cross Q2, or first identity of Y1 cross Q2 and then followed by Q1 cross identity of Z2. Okay. So the statement is, if Y1 and here Z2 are locally compact regular, then this composite is a quotient map, because each of them is a quotient map. Or you may use the other hypothesis here, namely Z1, say Y2 is a quotient map, Y2 is a regular, locally compact regular, and here Z1 is locally compact regular. So Y1 Z2 or Z1 Y2, or there is no necessity that both should be there. Y1 and Z2 or Z1 and Y2, that is the meaning of this one. Okay, locally compact order spaces, then Q1 cross Q2 is a quotient. Okay, now we come to the main theorem in this section, in this today's talk, and that is due to my care. So here is a partial converse, you may say. Start the regular space, or maybe you can state the Hausdorff space, it doesn't matter. Okay? Start the regular space, that's important. Then the following conditions are equivalent. So it's only partial converse. Regularity cannot be replaced. X is locally compact. Then every quotient map Q from Y to Z, the product identity of X cross Q is also a quotient map. 1 implies 2 is what we have seen. The converse is you have to 2 implies 1. So if this happens for every quotient map Q from Y to Z, if identity cross Q is a quotient map, X must be locally compact. This is much stronger than just saying that locally compactness under the assumption that you don't assume locally compact, the theorem is false. You can give that, for that you can just give a counter example, right? But here this is a theorem here. Okay, how do we prove this? By assuming that X is not locally compact, we will extract a space Y and a quotient map of Y to Z, Q, such that identity of X cross Q is not a quotient map. So this is the plan of the proof here. Okay, here we are going to use the exercise 10.9 fully. This is part of your preparatory assignments or practice assignments 10. Okay, this was not in the main part, but in the practice session. The main result is another not so familiar criterion for compactness. Okay, that's also part of this one. If you have not done it or tried it, okay, it is time that you should read the solution given. However, right now I can't afford that one. So what I will do, I will just recall this exercise here that I am going to use. Okay, exercise 10.9. Look at this part 4 here. Okay, so this is the main thing that I have to use. Let X be a topological space. Show that X is compact if only the following condition holds. For every family F of closed subsets of X with finite intersection property and linearly ordered by set enclosure. we have intersection of all elements of this curly F is non-empty. Remember, if I remove this linearly ordered by set inclusion, if I remove this condition, this and this one, this is a familiar condition for you. Namely, if every family of closed subsets of X with finite intersection property has a non-empty intersection. So that is a larger condition, right? So here we don't need all of them, only those which are linearly ordered by set inclusions. F1 containing F2, containing F3, you can take decreasing, just like in Cantor's theorem and so on. You can take increasing, but you can reverse the inclusion, you will get decreasing, there is no problem. But the point is, don't write F1, F2, that will give you that it is, mislead you, it is going to, countable. There is no countability assumption here, it's just a linearly ordered. So that is the whole point here. Okay, try to prove this one, but later on, anyway, we will give you a solution. The other thing is, this problem 3 here, let X be, this one, namely, problem 2 here, let L comma less than or equal to be a non-empty linearly ordered set with P belonging to P. Some point I have chosen, P belonging to L. Okay. Then there is a non-empty subset W of this L such that W is cofinal in L and restricted to W, it is, this ordering is well ordered. Moreover, the point P that we have chosen is the least element. So I don't use this full force. What I need is every non-empty linearly ordered set has a non-empty well-ordered subset which is cofinal. So this is what I am going to use. To prove this one, you will need 1. To prove 4, you will need 3 also, but that you read on your own. That's why they are the 1, 2, 3, 4. Okay, so let us go back to Michael's theorem. So as I told you, to prove the equivalence of 1 and 2, we have only to prove 2 implies 1. 1 implies 2 has been taken care by the previous theorem. So start with a topological space X which is not locally compact. We shall construct a quotient map Q from Y to Z such that identity of X cross Q or Q cross identity of X, doesn't matter, okay, is not a quotient map. Okay. Suppose X is not locally compact, at some point X naught belonging to X, then it is not locally compact. There is at least one such point at which it is not locally compact, right? What does that mean? There is a family A belonging to A. I have just, this A is nothing but just an indexing set, be a neighborhood system in X naught such that none of UA bar is compact. Okay. So this is the meaning of that X naught is not locally compact. There will be a neighborhood system such that UA bars are not compact. All right. What does that mean? Each UA bar is not compact. Means what? Now I am using this exercise 10.94 that I told you. For each A inside A, we have a family FA of non-empty closed subsets linearly ordered by inclusion of sets such that intersection of F intersection F belong to FA is empty. Okay. Since it is linearly ordered, I don't have to take finite intersection property. It will automatic, because I have said we have a family FA of non-empty closed subsets, linearly ordered by inclusion such that intersection is empty. Okay, so this is stronger than saying that there is some family with finite intersection properties, the intersection is empty. Okay, so this is where we have used XY 10.94. For convenience, we should index this family. I could have just written a FA. Each FA has to be indexed, right? So I fix an A, then I am indexing it by FT, T belonging to TA. Okay, so TA is the indexing set. That indexing set itself gets a linear order like as following, namely T is less than or equal to S if and only if FT contains Fs, reverse order. Okay, so T and S belong to TA. So in some sense I am taking this decreasing families. Okay, I can't say decreasing sequence and so on. This is not a TAs are not necessarily countable. They may be countable, they may be finite, I don't know, but they need not be countable. That's all. So T is less than or equal to S if and only if FT contains Fs. See, I don't need to float a TA, but this is just for the convenience, and it will clarify the proof later on. That's all. The FA itself is a family. So if you take an element here, two elements here, one is contained in the other. So that's all but I need that suffix instead of FA using members of FA itself, I am using T. So as soon as I have T belong to T, there is a corresponding FT. That's all. So that's why I have to take this indexing separately. From 10.92 about partial orders and so on, this linear order substance, we get a subset lambda A of TA which is well ordered and cofinal subset of TA. Okay, given any member of TA, say T, there will be some S, okay, which is bigger than T in this sense and belonging to lambda A. That is the meaning of cofinances. Okay, so these two things right now I have used. From now onwards we are just using just ordinary constructions here, quotient space and so on. Okay, so we add one extra point to each lambda A. Okay, you can call this as infinity A order, but I will call it as just lambda A. It's a very convenient notation. Take lambda A itself as your last element. This is the set. The set lambda A consists of elements of this one. You see, lambda A union lambda A is lambda A prime. Okay, just one extra element. That extra element itself is lambda A. All right. So take this. Now you extend the linear order on this well order on lambda A to the entire lambda A prime by just declaring this lambda A as the maximal element, the one maximum element actually. The lambda A is bigger than or equal to all T belonging to lambda A. That's the meaning. Now you take the order topology on lambda A prime. Because there is a maximal element also, this will be a compact Hausdorff space. It's always Hausdorff space. The compactness comes because of this extra point that you have taken. It's like a 1-point compactification. Okay. Now put y equal to disjoint union of all these lambda A's, where A ranges over A, starting with this neighborhood system which is indexed by A. That A comes here. Okay, disjoint union of all these compact sets. Okay, this is a huge set. This Y itself is not a compact space. All right, with disjoint union topology. Disjoint union topology. On each lambda A prime, I have the order topology. Having taken this space Y, now I construct the quotient space Z by identifying all these extra points lambda A. Lambda A will be equal to lambda B for A and B inside capital A, for all A and B, one single point. That I will denote as Z0, and the quotient space I will denote by Z. I repeat, how is Z constructed? No other elements of lambda A prime are disturbed. Only the extra point that you have taken lambda A. All of them are identified together to a single point. That is Z0. So this is a quotient map. So this quotient map has the property that on Z0 you have all these lambda A's, the fiber. Everywhere else it is a 1-1 map. Inverse image of every other point is just one single point. Okay, so this is the quotient map. That means this is a quotient function. So we give the quotient topology on Z. That's all. We claim that Q is as required. It's a quotient map such that identity of X cross Q is not a quotient map. So two things we have to prove. Okay. Actually, we have to prove only quotient map is fine. It is not a quotient map. For that, we have to prove something. Okay. So here is a preparation for that. For each A inside A, what we have? And each lambda inside lambda A prime. That means what? Lambda A prime has one extra element of capital lambda A, right? So you can take that for the lambda. Put E lambda equal to intersection of all F sigmas where sigma is less than lambda. Okay. So if this lambda was capital lambda A, then what is this intersection? This intersection will be all these FTs, right? Where T belongs to this lambda A, not lambda A prime. And what was the assumption? Assumption was that, remember this assumption, intersection is empty. If I take anything smaller, then what happens? Because it is a decreasing sequence, okay. In any case, first of all, since the intersection of closed subsets, each E lambda is a closed subset of UA bar. Okay. E lambda, remember these are all subsets of UA bar. E lambda is contained inside F lambda, okay, and F lambda is not empty if lambda is not the whole of lambda A. Each E lambda contains F lambda here already, okay, because E lambda is what? Intersection of all these things. It contains the next one because all of them contain F lambda, right? It's a decreasing thing. So, and F lambda is non-empty. Every member is non-empty. So, if this lambda is not the last element, then this is non-empty. If lambda is last element, then of course this is empty. Okay, so that's all elementary observation. Now we want to show that the map identity cross Q is not a quotient map. What we do? We take a closed subset of the total space, which is the inverse image of some set, okay, that some subset below is not closed. Okay, so that's what we want. So put SA for each A, SA equal to E lambda cross lambda. This is X cross lambda A. Okay, where this lambda A's are inside only lambda A. I have not taken the last the maximal element here. Put SA equal to E lambda cross lambda. So each of them is a closed subset of X cross lambda A now. Okay, because this lambda A has the order topology, singleton sets are closed. There is a Hausdorff space. We claim that SA is closed subset of X cross lambda A prime itself. The whole thing is a subset of lambda A X cross lambda A prime, because lambda A prime is a larger space than lambda A. In particular, it is a closed subset of X cross lambda A also. See, it's easy to see each of them is a closed subset, but why the union? This union is an arbitrary union, right? Over all the lambda. But we want to say that that is also a closed subset. So how do you prove that? Take a point X lambda which is not in SA. Okay. Something is, this want to show that this is a closed subset. The same thing as complement is open. All right. So start with a point X lambda which is not in SA. What is the meaning of this is not in any of these? It's a union of these things, right? So this means that X is not in this first coordinate is not inside E lambda, right? If X is inside E lambda for any of these lambdas, then this would have been inside SA. This means X is not in E lambda, but E lambda is what? Intersection of all F sigma, where sigma is less than lambda. If something is not in the intersection, which implies that there exists some sigma less than lambda, such that X is not in F sigma, right? Let R sigma be the right open ray inside lambda A prime. Remember, these are all well ordered subsets. The right ray, etc., left ray, etc., all make sense. Okay, so once you have got some sigma here, R sigma means what? All those lambdas which is bigger than sigma. So that is your lambda A prime. That is your R sigma inside lambda A prime. Then F sigma complement, F sigma is closed subset, F sigma complement will be an open subset cross R sigma, which is also an open subset. F sigma complement contains X because X is not in F sigma, and R sigma is an open subset, okay, which contains lambda. So this is a neighborhood of X lambda in X cross lambda A prime. All right, it's easily checked that this SA intersection, this open subset is empty. What does that mean? That this is contained in the complement of SA. So what I have shown here is that X comma lambda belonging to SA has an open subset which does not intersect SA at all. Open neighborhood, it does not intersect SA at all. That means this complement of SA is open. That is the whole thing. Okay. So why this is empty? For this you have to use the elementary fact here that Ft is bigger than Fs if T is less than S. Okay. You take a point here, it cannot be inside SA for any of them is all that you have to show. So we have got a set here which is a closed subset of X cross lambda A prime. All right. So in particular, it is a closed subset of X cross lambda A also because it is contained in X cross lambda A. Now take S to be H of SA and take union of all over all A inside A. Okay. See, each SA is a closed subset of X cross lambda A. Disjoint union of those things with the disjoint union topology is Y. Therefore, disjoint union of all these SAs, that is a closed subset in Y cross lambda, sorry, Y itself. Y itself is the disjoint union. There is no Y cross. So that is a subspace Y, right? So Y has this disjoint union of closed subset, that's a closed subset. Okay, in the disjoint union topology, there is no problem. All right, but S is its image, H of SA, as A rings over A is the same thing as H of all these disjoint unions. That is a subset of X cross Z below. Okay, because first coordinate I have taken as X here. So we claim that H inverse of S is a closed subset of X cross Y, which is nothing but, I just told you, disjoint union of all these, all these SAs, which is a subset of X cross this Y here, not Y, X cross Y. Okay. Yeah, so what we have got is that H inverse of S is closed. This is why we already seen, but S is not closed in S cross Z, which will show that H is not a quotient map. H being identity of X cross Q. All right. So again, I am repeating here. H inverse of S intersection with X cross lambda A prime is these SAs. Therefore, they are closed. So H inverse of S is closed. Okay, this I have repeated, I have already told you. All that I need to show is that its image inside X cross Z is not closed. Okay, for this we want to check that X naught comma Z naught is not in S, because Q inverse of Z naught is all singleton says A inside A, right? However, we claim that X naught Z naught is in the closure. This closure is taken in S cross Z. Something is in the closure and not inside S, just this is not a closed set. That's all. Okay. X naught comma Z naught would have been inside X. See what is S by definition is H of SS X cross Z. Okay, it will never hit the point Z naught at all. Right, that is the whole idea. So for this, start with X naught Z naught inside U cross V, where U is open in X and V is open in Z. I want to show that this is in the closure means what? Take any neighborhood. I could take standard neighborhoods, show that it intersects S, that's all. Okay, so take a basic neighborhood U cross V of X naught Z naught in the product topology. Okay. Let A belong to A be chosen such that UA bar is contained inside U. So what I am using here, that this family of UA bars is a neighborhood system at A. So if U is a neighborhood system at X naught, sorry. If U is a neighborhood of X naught, there will be some A such that UA bar is contained inside U. Okay. This is a closed system of closed neighborhoods. None of them is compact. That is how we have chosen them. Note that this lambda A is in Q inverse of V intersection with lambda A prime. The top thing will be there because Z naught is there inside V. Okay, so Q inverse of V will have this lambda A prime, lambda A itself, which is in lambda A prime. And hence, we will have some lambda belong to lambda A, that means we something less than that one, such that Q lambda will be inside V, because it's a neighborhood inside this lambda A prime. If Q inverse of V is open, right? Q is a quotient map. It's an open subset, contains this point. This is the maximal element. So there must be some right ray, right, which contains that, starting from lambda. Maybe something smaller than that. So you can take some lambda beyond lambda, as I said. This Q lambda is inside V. Or you can say that something less than lambda, say lambda prime open to capital lambda A close, that entire thing is contained inside Q inverse of V, which is the same thing as Q of that is inside. It follows that now H of E lambda cross lambda, if you come down under the quotient map, okay, is contained inside U cross V. See, this H just identifies all these lambdas when lambda is smaller to the same elements here. There is an identity map. So that will be inside U cross V intersection S. Okay, which completes the proof. You just recall that S is all such H of SS. All right. So this E lambda, H of E lambda cross lambda is inside U cross V. That is a perfectly example. So I will just make this remark. We kept the statement of the theorem as simple as possible, unlike the original statement given in Michael's paper. Indeed, the quotient map that we have constructed satisfies a number of properties. Let us say it belongs to a special class capital P of quotient maps. This class capital P is the class of all quotient maps from X to Y, where X is a disjoint union of compact Hausdorff spaces, and fibers of Q are all singletons except one fiber, which is discrete closed set. So this is actually, this X is our Y and Y is Z. I have deliberately changed them because you should be able to do that on your own also. Okay, what is the quotient maps are very peculiar. Only one point inverse image may be having too many points. Rest of the points inverse image has consists only one point. Such maps you take, and such maps, if for all such maps identity cross is a quotient map, okay, if you take then X will be locally compact. That is the statement that we have actually proved, but we don't want to insist on that one. So we can add these three also in the theorem. So 1, 2, 3 are all equivalent. This will be much weaker statement than 2. I mean, looking, because this is a subclass. Okay, that's all. Thank you. Next time we will do something else.